Okay, so good morning once again. Um, we are going to look at the periodic table. Um, for me, I take three topics as the backbone of chemistry. Which
Okay.
topics are they? One, we have to talk about bonding. Bonding is very important. You have to make sure you understand it. Two, atomic structure. Atomic structure is also very, very cardinal in our in
Mm,
our chemistry world. The third one is the periodic table.
yeah.
How and why are these three topics important? Here are the reasons. Chemistry, from the introduction, they told us that is a branch of science that deals with matter as well as the changes that matter undergoes. That was the definition of chemistry. Down there, we also were told that matter is made up of three subatomic, is made up of three particles, which are molecules, atoms, and ions. So, meaning for the entire chemistry to be understood, we have to know matter. We have to know what matter is made up,
Mm,
as well as the changes that matter undergoes. That's why we have got two types of changes. We have got a physical change as well as a chemical change. Now, from the chemical change, that's where now the entire chemistry goes because we have chemical reactions.
yes.
So, within that, we understand that one of the things that matter is made up of are atoms. So, within the atoms, we have to understand the structure of an atom.
Yes.
But these atoms are atoms of the elements. Where do we find the elements? They are on the periodic table.
Periodic table.
And when these atoms or when these elements react, what do they form? Bonding.
On.
So these are the three topics that you have to understand. Any other topic that will be difficult for any person down the chemistry lane, you have to know that one of these three has not understood properly.
Mm,
Because even when you say that the other particle that matter is made up of are ions, ions are actually atoms when they form when they become charged. So
yes.
basically, they're atoms. Molecules, these are substances that are formed when two or more elements combine. So we are also talking about the
Mm,
atoms and all the way atoms bonding, atomic structure, periodic table. So with
yes.
all that said, I want you to understand the thing that we're looking at.
Okay.
So the periodic table, I will have to tell you this, that there are a lot of tables in science. In the scientific world, there are a lot of tables. Let me give you
Okay.
one of the tables that we have. When we were just born, we were given, how do you call those tables? The under five card? Uh-huh.
Yes.
On the under five card there, the people in the health fraternity, each age that a baby is attained, they should have the range of the weight. But I don't know how these people in health, that weight is measured in kg. I need to teach them that weight is measured in newtons. A 2 years old baby, a 2 years old baby, they have a certain range within which they would say this child is normal. If it falls below that, they will say maybe the child is suffering from malnutrition.
Mm,
And if that goes above the normal, they will say maybe the child has got obesity. So these tables are the ones actually that guide us. There's certain information that we may not manage to keep within our heads. So when we feel that information is needed, it is written somewhere where we can go and get it. talk about the people in the environmental monitoring, such as Vazema, such as ZABS, even them, when they are making a drink, there is a certain amount of sugar that must be contained in there. So they actually have tables. These are the tables that guide them in many ways. Actually, as you go up, you find a lot of tables in chemistry. We have got IR table, we have got mass spec table, we have got character table. There are a lot of tables. These tables contain information which is very vital, which at times we might need to get from them. Now, from the periodic table, what information do you have? We are saying that the periodic table, some books call it a table, others call it a chart. Now, whatever table that you draw, whatever chart that you have, there must be something contained in there. But within this chart we are calling a periodic table, what we have are elements. These elements are not just mumbo jumbled. There is a systematic way in which these elements are arranged. How are they arranged? They are arranged in the increasing of the atomic number. So you see, that's where I was saying that the basis of chemistry is atomic structure. Because from the atomic structure, you should be able to understand what atomic numbers are. You get the point, huh?
Yes.
So even in as much as we're trying to learn the base, the one of the basis, which is the periodic table, you still need the atomic number so that you know what this the atomic structure, so that you understand what the atomic number is. But maybe let me give you this highlight. Any element that we are going to find, actually, the nuclide notation from the atomic structure is written as X. Then you've got A here, and here you've got Z. These have got meanings. This has got a meaning. This has got a meaning. This has got a meaning. What are their meanings? The Z, the A represents the mass number, also called nucleon number. The Z here represents the atomic or proton number. They are the same. And then the X here represents the symbol of an element. So there are three things that you can find from any element that you find, though there are some elements whose mass numbers have not been quantified. But the basis of it all is that any element that you find, any atom that you find, there should be a smaller number that is written on the left bottom. There should be another number that is written on the top left. Actually, the one that is written on the top left is bigger than the one at the bottom, though it depends on the periodic table that you are using. But the current one, the basic one, is the one that has a bigger number on top. And any element has got a unique symbol. And these symbols, we are not learning them now, we learn them from the atomic structure. So you see, chemistry is connected. You can't talk about anything here minus referring to something you learned yesterday. So we have understood what is found on the periodic table, and we have understood the format that they use to arrange. So meaning when you're given any two elements, for as long as you know the number which is written here, we are calling the atomic number, you should be able to know what that element is, also where it should be. So when you're given two, you should be able to know which one should be on the right, which one should be on the left, which one should be up, which one should be down, just by considering this number. So this number actually is very, very important. Now, so this is what we're saying, that atomic number is a property. It's the atomic number that we use, nothing else, not the symbol, not the color, not the density, not the viscosity, not the melting point, not the alphabet. What we follow is atomic number in the placement of these elements on the periodic table. So roughly, these are the elements that we have. Forget about which ones are metals, which ones are non-metals, and things like that. Forget about them. For now, we're just having an overview of these elements that are here. Though the best would have been that periodic table where elements are indicated, as well as their mass numbers. They'll definitely find another one down the line. So do you have questions, or maybe I can move on?
No, you can move on.
Thank you. Now,
Okay.
with all that said, let's maybe just journey through the periodic table. So we have these things, though we haven't yet been introduced to them, these which are written in Roman numerals. They're actually increasing as you move from left to right. I hope you haven't forgotten your Roman numerals a concept. Otherwise,
No.
you will be termed as a senior student who forgot primary school concept. So this is one, but they are not written as the numbers like this. No, they are written in Roman numerals. So we have a 1 here, we have a 2, we have a 3, we have a 4, we have a 5, we have a 6, we have a 7. We don't have an 8. We go back to 0. And there is a reason to that. So these ones here are the ones that are called groups. So because these elements are a lot, the way we can study them, we can't put them in one basket and start studying. No. Because even when you go to ShopRite to buy, when they are packing things in plastics, they categorize. The foods are put in separate plastics. The detergents, soap, things like that, they are also put in plastics. They are categorized. So even these elements, in as much as they are all grouped in one table, actually they are in groups. These groups have got also particularities that we follow. So we can say in group 1, these are the ones that we have. So we've got lithium here, we've got sodium, we've got potassium, we've got rubidium, we've got caesium, we've got francium. These are in group 1. Group 7 here, we've got fluorine, we've got chlorine, we've got bromine, we've got iodine, we've got astatine. Group 0, we've got helium, neon, xenon, krypton, no? Helium, neon, argon, krypton, xenon, and I don't know, I've forgotten this. I don't know if it's radon.
Radon.
Radian. Yeah, I don't have my periodic table. I'm just trying to remember the few elements that I know. So that is it. So all these elements that are put in a particular group, there is a property that they follow. And that property, we need to understand it. So that in a moment where we have got a lot of elements, and then they ask us to say which one of these elements can be put in one group. So you should be able to know the thing that they used in grouping these elements. Now, unfortunately enough, these elements here are not given a particular group for your chemistry. Are not given a group, but for pure chemistry, allow me to confuse you just a little bit. For pure chemistry, this is how they number it. For pure chemistry, this is 1. Pure chemistry, of course, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8, this is 9, this is 10, 11, 12, 13, 14, 15, 16, 17, 18. With them, they go up to 18. That's for pure chemistry. And there is a reason for that. So I was saying that there's a particular order that they follow when they are arranging these elements. So for pure, the order that they use and the one we use in science are different. So in a moment in your field of endeavor, you get to do maybe that science that requires you to do a bit of pure chemistry. You should be able to remember this. Oh, that guy talked about this. But for now, we only stick to what we know. What we know is that these elements are just called transition elements. And we'll discuss more. Actually, the periodic table, you have to do the discussion of all elements on this thing. And when you go to university, you have to do a six months course just studying the periodic table, which we call the chemistry of the periodic table. Because from the chemistry of the periodic table, that's where that branch of chemistry you talked about as inorganic chemistry. It comes actually, it starts as the introduction, you say, it's in, oh, the introduction is it, the chemistry of the periodic table. Then when you clear that, the next thing, that's where now you have an inorganic chemistry. So that's why I was saying that this thing we are doing now is very, very. So we'll come back to this table now and again.
Yes.
We can move on to something that's ahead of us. It's the same thing that I was talking about here. I've already explained that when you have this, I'd already explained that the A represents the relative atomic mass or the atomic number, and then the X represents, or the A here represents, then they switched this one they switched. What we have here is the atomic number. Let me just show you something. We'll come back to this. I just want you to see this. I just want you to see that. Have you seen that we have a bigger number on top?
Yes.
And we have a smaller number at the bottom. This is the mass number, relative atomic mass, supposed to be up. Relative, the mass number supposed to be up. Then the atomic number down. Yeah. Now this guy is, I'm sure that's a thing that we have here. So we have the one on top is the atomic number, no, the mass number rather. Then the atomic number here, the X represents the symbol of an element, which they are calling the atomic symbol. So if we are to move on, we are saying now that these elements that are on the periodic table, they are arranged in increasing of the atomic number. Then, why are these elements placed in groups? Those that are placed in groups, like I was mentioning downward in group 7, where I've got fluorine, chlorine, blah, 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 blah. All these elements that are in a particular group have similar, they may not be the same, but they have similar chemical properties. Meaning, the way this element which is here reacts, it's similar to this, it's similar to that, similar to that. But they may not be exactly the same, but there are some similarities. That's what this point is saying. Now, those elements that are put in the same group, what do they follow? Remember what I told you, that our chemistry or our science, the property that we follow in arranging those groups going up to group 0 is different from those ones for pures. Now, for both pure as well as science, what they consider is the electronic configuration. Both, it's electronic configuration. But why are we different? So the difference is how we write the electronic configuration, and I will show you where we. Sorry?
I'm sorry, I have a question.
Yes.
The electronic configuration, isn't it how the shells or the different layers are arranged?
How the electrons
The atomic.
how electrons are arranged in the shells. That's the configuration. That's why we are calling it electronic. It's to do with electrons. So they are the arrangement of electrons that we consider. Okay. Have I answered the question?
Yes, you have.
Now, the challenge or the difference is how do you write your electronic configurations? For pures, they are written differently. For science, they are also written differently. So our duty here is trying to see how we can look at the difference. So here we go. Down here, we are told that, okay, yeah, I think now this one is a bit okay. Yeah, it's okay. It's okay. So now let's look at something that I might have not mentioned here. The word here, periods. Periods. How many periods do we have? 1, 2, 3, 4, 5, 6. So this is 1 here where the helium helium is. So 1, 2, 3, 4, 5, 6, 7. Now these, what do they represent? Because we are saying groups, we consider the electron configuration, and much more is to be said. What about the periods? The period will also do the electron configuration. But from the electron configuration, let me give you an example of aluminium. Aluminium, it's capital A, then small l, the atomic number 27, the mass number 13. So what we consider here are the number of electrons. So electrons here are 13. So how can we write our electron configuration in our science way? Now I want you to now pick something here where the difference lies between ours as well as the pure. So ours, this is how we write. We're going to say it's 2, 8, that's 10, 3. This is how we write for aluminium in our science. But for pures they write like this. Allow me to use maybe even the keyboard, yes. For pures, this is how they write. There's 1s, there's 2s, there is 2p, there is 3s, and there is 3p. This is how they write. But we can see that electrons that we are dealing with, they are 13. So the first s orbital will get 2, the second s will get 2, the second p will get 6. So together that's 10. And then the s will get 1 or get 2, then the p gets 1. That's how you write the electronic configuration of elements in pures. Now from here, what can we say? This aluminium which is here, I want you to pay attention. This aluminium which is here, what can we say? Number one, aluminium has got how many electrons in the outermost shell? In the outermost shell, they are actually, the electrons in the outermost shell are actually 3. That is why it is in group 3. But for pures, we can see that we have got 3s and 3p. So you need to understand what these letters represent. The S, which is a singlet, the P, which is a triplet. What does it mean? And those things. So you see now, that's where now we differ, science and pures. Because ours right here, we are done. And we said it's 2,3, or it's 2 and 8, which is making 10. But here this 10 is splitted into 3 streams. There is the S, which are having 4, then the P gets 6. but that information is not here. So have you seen where we differ in our configuration? So even the grouping, that's how we get to differ in some ways. So we can now start discussing the periodic table in details. And what we are starting with are the periods. What are the periods? Why are elements arranged like this? That's what we are looking at. So maybe just to give you a hint from the configuration that we've just drawn, how many shells are there? We use the first shell with the 2 electrons. We use the second shell with 8 electrons. We use the third shell with 3 electrons. How many shells did we use? We used the 3. Therefore, aluminium should be in period 3. So the first period is that, period 1. The second period, period 2, and aluminium is in the period 3 because the electrons that it has can only occupy 3 shells. So that is a property that we follow. So if we can move to now the details of our learning, we are saying we are starting with a period. What is a period? So we're saying a period is a horizontal. So the word here is a horizontal from left to right, right to left. The horizontal rows of elements in the periodic table. I'll go back to my camera so that I show you something. So we have these lines here that we are calling horizontal rows. Then we also have these ones here that we are calling vertical rows. Oh, I've even switched. Forgive me. So we have these ones that we are calling vertical columns rather. These are the ones we are calling vertical columns. And these ones here are the ones we are calling horizontal rows. So when you're talking about a period, you're talking about counting these ones. How many are they? 1, 2, 3, 4, 5, 6, 7. So these are the periods we are talking about. So it's a horizontal row. But how many did we count? There are 7. So for the period, you can write the actual number is 7. But for the groups, why do we do that? So that we provide the distinct. We distinguish the numbering of periods and the numbering of groups. Some are written as Roman numerals, others are written as just numbers, digits. So when we say elements are in period 1, what does it mean? It means this element only has one shell. All the electrons that it has can only fit in one shell. Which elements are these? Hydrogen. The structure is 1-1 and the configuration will just be 1. The next one is helium. Helium, it's He4 and the 2. But we are talking about these electrons can only be filled in the first shell and all the electrons are done. The moment you go to lithium which is got 7 and 3 here, it will give us panic because the first shell is already full with 2 electrons. It is the second electron, so the second shell, that's where the remaining electron will fall. That's why we're saying that in group 1, we only have 2 electrons, 2 elements. These are the only ones that have got electrons that can fit in the first shell. Then what about group 2, or rather period 2? So we're saying periods 2 and 3 contain 8 elements and each are called a short period. Now let me show you what I mean. Which elements are those? So for group 2, the first shell should only have 2. The second shell, the maximum it has, it's 8. So meaning the last element in period 2, the last element in period 2 should have 10 electrons. The last element in period 2 supposed to have 10 electrons, and the first element in period 2 supposed to have 3 electrons. Are you getting the point?
Yes.
So let's check out. Let's check out. We're saying this is period 2. Allow me to remove this thing that's written here. This element which is in period 2 is a helium, and for that we can see that has got 3 electrons. And the last one in, fortunately I can see, the last one, okay, I'll just assume that I'm in position on the right thing. So the last one on in group 2 supposed to have how many electrons? 10. Have you seen? Can you see it? The paper is very far. Oh, good. So this is what we have. So group 1 here and group 2. And we can see that group 2, the electrons that are there are 10. You get it? So this is group 3 and things like that. So that's how we understand the groups, or the periods rather. So each element that is given, the best that you can do, draw its configuration. When you draw the configuration or write the configuration, then from the number of electrons that it has, we can tell how many shells that will be occupied. So the number of shells are the ones that are represented by the period. So we can have an element like potassium. Potassium, symbol is K, it's 39 and 19. So without looking at the periodic table, let's write the configuration. Then from the configuration, we should be able to tell the period where this element is. So the first shell 2, the second shell 8, the third shell 8, this is already 18, because this is 10 plus 8, 18, but we have 19. So we only have 1 remaining in the last shell. So how many shells do we have here? Help me count them. 1, 2, 3. How many shells?
4.
So we expect this element to be in period 4. Let us check out. So potassium is in period 4. I can count. Period 1 is this one here. This is period 1, because that's where this element is. Have you seen? This element here goes all the way up to that. So this is period 1, period 2, period 3, and this is period 4 with 19 electrons. We can even see them there, 19 electrons. So that is what we have. And this trend goes on and on. You can pick any element that you want. You can pick any element that you want, and when you write the configuration, you'll find that this thing agrees. But the trouble now with our science. I like talking about the positive and negative things of our science. Let me show you the trouble. Let me show you the trouble. Look at this element, scandium. After calcium, then this one, scandium. When you look at this scandium has got how many electrons? 21. Okay, maybe I'll talk about this when we look at the groups, because the groups, that's where the trouble is. The period agrees, but the group, there's a limitation of elements that agrees to our science. The other elements don't agree. So let's see what we got. So this is what we are saying. The information here is just repeating. It's talking about calcium, which has got 20 electrons. First shell 2, second 8, third 8, fourth 2. So 2 plus 2, 10. 2 plus 2, 10 gives us 20 for calcium. And we are saying that it must be in period 4. Now, we are saying that the elements that are placed in the same group have similar shapes. What about those that are placed in the same period? Do they have similar characteristics? Let us see. Some of the things that are common in the elements that are in the same period. We haven't gone to groups in the same period. These trends, the characteristics, we actually call them trends, or the trends, the properties. There are some properties that we are likely to have as you move across the periodic table from left to right. The same elements, these ones here, potassium, calcium, scandium, all these vanadium, all chromium, manganese, ferrous, copper, cobalt, all those all the way up to here. What are some of the properties that we are likely to meet? The properties that we are likely to meet are the following. We are saying, as you move across the group, across the period from left to right, there are properties that are likely to be the changes in the properties. One, the metallic nature, the metallic character decreases. They change from metals to non-metals all the way up to inert. What does it mean? I'll be explaining and demonstrating gladly. I have a project with me. So we're saying that the metallic property changes or reduces. So we have from metals to non-metals. So from left, we have this one, which is lithium. We're in group 2. We have lithium. Then we've got the next one is beryllium. From there, we go all the way up to, so these ones that we have here are metals. Lithium, beryllium are metals. Our next element will be here, which is boron, carbon. Now, boron here is a non-metal, or is a metal. Boron is a metal. And then carbon is a metalloid, stands in between metals and non-metals. So metals are done. Here, nitrogen is a non-metal, and we know it's a gas. We have oxygen. Oxygen is a non-metal, it's a gas. Fluorine is a non-metal, it's a gas, until we go to an inert gases. So all these that are here up to somewhere here, all these are inert gases. So we have non-metals on the right, and we have metals on the left. That's why we are saying that as we move from the left where we've got metals, on the right, we are likely to find non-metals. This is the point which is here. Are we okay? Then the point number 2, the electronegative decreases or increases. The electronegativity increases. Now, what is the electronegativity? We're talking about the ability, relatively, of atoms to attract a pair of electrons in the formation of covalent bonding. Remember, covalent bonding is only possible when elements are sharing. So we understand that the ones that share electrons are non-metals. So because what we have on the left are metals, and metals do not share electrons, so they don't have a larger value of electronegativity. They don't share electrons, they are not electronegative, in short. As we go to the right, that's where we have got those non-metals that share electrons, and that's where we have elements that have the tendency to receive electrons, and those elements are the ones which are said to be electronegative. So as you move from the left to the right, the electronegativity, the ability of elements to act as non-metals, the ability of metals to receive electrons increases. That's the point which is here. Point number 3 says the atomic number increases. Now you see, when you are counting, even here, we are counting moving from left to the right. and our numbers are increasing. Okay, so as we place elements, we start placing from the left going to the right. And because we are saying that elements are arranged according to the increase in atomic number, we expect the atomic number to be increasing successively. Point number 4 is talking about the number of shells. The number of shells remain the same for as long as elements are in a particular period. If elements are in group in period 1, the number of shells will be 1. If elements are in period 2, the number of shells will remain 2. Ask questions before we move on to the next part.
So far, I've understood on the same page.
Sorry?
I'm saying so far, I've understood you on the same page.
Okay, thank you. So we can maybe go to the next part, which should be the last one, because I'm rushing into town. So this is just indicating how all that is done. We've got our sodium here, which is Na. The sodium comes from the Na comes from nandium, which is 23 here, and we have an 11. So these are the electrons that were distributed in their respective shells. 2 plus 8, 10 plus 1, that is 11. We expect them. Forget about the valences. We haven't yet looked at groups. I wonder why they even included this. We expect this sodium to be in period 3, magnesium to be in period 3, aluminium to be in period 3, because they have the same number of shells. So because actually the numbers are increasing, this is 11, 12, 13, these elements are supposed to be following each other. Let me show you what I mean. Because the atomic number of these elements they have given us are successive, are consecutive numbers, we expect them to be in the same period. So they started with the sodium. So we have our sodium here. Started with the sodium. So they started with sodium here. Sodium Na 11. They went to magnesium 12. Then they went to aluminium 13. So the increase in the atomic number is in that way as you move from the left to the right, agreeing to one of the points that was raised up there. So this is the same thing they did even for these elements. Forget about valences. Valences are talked about under groups. So this is that. So having talked about the groups, we can now go to, having talked about periods, we can now go to groups, and that's where we'll end. If periods were a horizontal row, we expect the opposite to be the case. If it's not horizontal, then it must be vertical. If it is not a row, then it must be a column. Remember when we're talking about matrices, this is A, this is B, C, D. We're saying multiplication of matrices is done in rows. So these are rows. That's why we said horizontal row. Rows per column. So this is what we are calling a vertical column, as our description entails. So we're saying that these are vertical rows of elements in the periodic table. With them, according to what I said, there are 8. But though we don't have an 8, the 8th one is given a 0. Now here is where I'm going to explain why a 0 is used and not 8. Because we started from 1, we expect the last one, because they're 8, to be the 8th, but it's a 0. And here's an example explanation. So saying that groups that are labeled in Roman numerals like I'd indicated, but unfortunately, 0 does not have a symbolic expression in Roman numerals. So the 0 comes out that way, unfortunately. So it's only 0 which is that stubborn. Even when other elements are trying to bend according to the Roman numerals rules, the 0 says, I'm going to come out the way I am. So Now we're saying that how do you get to know the group in which the element is? You write the configuration. Now from the configuration 2,8,3, which is aluminium. Maybe let me have something different. From this element we have, which is sodium, how can you know the group? We are away from the periods. We are now on groups. We are saying that the position of an element in the periodic table, the period, is determined by the number of electrons in the outermost shell, the last shell. And these are the elements that help us to determine the valence that an element has. So these are called valency electrons. These are the elements that help us to determine the valence of an element. So this shell is called the valence shell, and the elements that are contained in there are called valence electrons. So we use the valence electrons to tell the group in which this element is. That's why I said here we are going to skip it because we had not yet looked at the group. So we're saying that the number of electrons in the outermost shell are equivalent to the group. Exactly, equivalent to the group. So the number of electrons in the outermost shell will depict the group in which that element falls. So from the configuration, we can write the group. We can also write the period. Now, I remember saying that certain elements do not agree to our usual configuration and grouping. And the element that I talked about is this element that comes immediately after calcium. This SC. Where are you, my guy? So SC is here. So this SC is scandium. Scandium has got 21. Now let's see. We expect it to be in group, okay, maybe away from that. We can maybe go to the one that is below chlorine, which is the bromide. So bromine, according to the grouping that we have in our science, supposed to be in group 7, meaning we expect it to have 7 electrons in the outermost shell. But it will not agree with bromine. It will not. I know what I mean. It will not. How many electrons does it have? Bromine, 35. So let's write the configuration for bromine, 35. So Br 3542 or 3542, I think. Br 35 8. The one for 42 is SC, scandium. So let's write for 35. So I'm going to have 2,8, that's 10, 8, that's 18, 8, so that is 18 times, this is 18 times 3, that's 18 times 3, that is 24, 24 plus 2, that's 28, right?
It's 26.
24, yes, 26. Then plus 8, how many are we going to have? So this is 32,
34.
34, meaning the last one is 1. We are already 35. This gives us 32 plus 2, 34, plus 1, 35. So from what we have in our configuration, we actually expect bromine, because it has got 1 electron in the outermost shell, we expect this bromine to be in group 1. But guess where this bromine is found? Bromine is found actually in group, it's found here, in group 7. Group 7 here, down here, that's where we find bromine. But according to our science kind of arrangement, bromine is supposed to be in group 1. So it's at this point where we're saying that our science kind of configuration totally disagrees with the pure one. The pure one, the system they use it agrees to each and every element that you can think of. Now, what are the things you are likely to witness as you go down the group from the bottom from the top to the bottom? The first thing is that the metallic nature increases. Why does it increase? It's because the number of electrons, the number of neutrons, and the number of protons increase. So as they increase, you find that even the density changes. Even the mass changes, because density is a mass per unit volume. So for the same amount of volume, if you have an element which is a fluorine on top there, with the only 19, the total of 19 protons and neutrons, only 19. And then you also compare it with bromine, which has got 80. The combination of protons and neutrons gives us 80. You'll find that bromine is likely to be denser than chlorine. And in as much as we know, gases are lighter than metals. So as the mass number increases, even the density, the viscosity, and the metallic character also increases as you go down the group near a point. Point number 2, the atomic number increases. That's very true, because we are saying as you group them, we are going to be going in this direction. So this is period 1, period 2. So meaning, if we're talking about groups, the one that is here has got a smaller atomic number. The one that is here below it has got a bigger atomic number. That's what we are saying, they increase. The elements in the same group have the same number of electrons in the outermost shells. That's the reason as to why they are actually positioned in those shells, because the number of electrons in the outermost shells are the same. Now, for non-metals, now we're talking about, okay. We're saying for metals, this is the last point. For metals, which ones are metals? Metals are the ones with electrons in the outermost shells, 1, 2, and 3. These are metals. So these are groups. So the number of the groups, the number of electrons in the outermost shells are actually equal to their valences. If it has got 1 electron in the outermost shell, it is in group 1 and it has a valence of 1. If it's in group 2, like calcium, magnesium, it's got 2 electrons in the outermost shell, has a valence of 2. Aluminium, which has got 3 electrons in the outermost shell, has got a valence of 3. What about 4? 4 also is in the similar case, but this is not a metal. That's why I didn't include it, because in that thing, they are only metals. But what about non-metals? They start from 5, 6, 7, and 0. Now, why are we insisting on having a 0? Let me explain. Talk about helium. The first element in group 2 has got 4 and 2. So first, let's arrange them. The first shell is 2. After this shell is full, we don't have anything here. We have a 0. Let's talk about lithium. Lithium here, 7 and 3. When you arrange them, we're going to have 2. After the first shell is full, the next one is 1. That's why it's in group 1. Which other one we can talk about? I can talk about neon. Neon, Ne, 20 and 10. Let's fill up all the shells. This one is full. This one is 8, also full. Now, the moment this one is full, the next thing, we don't have anything. So if we had gone by the grouping of saying, no, they are in group 8, they are in group 8 because the last shells have got 8 electrons. What about helium, who has got 2? It will be unfairly included. So after the shells are full, how many are a surplus in the other shell? So here we don't have anything, group 0. Here we don't have anything, group 0. So if we had gone by group 8, then helium was not supposed to be there. And because its outermost shell is full, it belongs to the same category where these other elements are. So now we're saying that for non-metals, the valence says the number of electrons, if they are 5, you get these 5, you subtract from 8. 8 from 5 will give us 3. Oxygen has got 6 electrons in the outermost shell, but its valence is 2. It's 8 minus 6, which gives us 2. Chlorine, fluorine, bromine, iodine have got a valence of 7. So when this 7 is subtracted from 8, we're going to have the valence of 1. And these ones do not have any valence because the number of electrons after the shell is full, there's nothing that goes in the other shell. So they don't react. They are combining power, their valence is 0. So the summary of the valence as we conclude will be that. I'm going to put up a table. This table will be like this. If you're talking about the group, okay, let me talk about valence electrons, meaning the number of electrons in the outermost shells. We're going to have it there. Then we're also going to include the group in which this element is. A group. Then we are also going to talk about its valence now. So the valence shells or the valence electrons, we're just talking about the number of electrons in the outermost shells. And then the valence, the number of bonds that is likely to form, or the number of electrons it can gain or it can lose. It also pointing back to bonding. So if this element has got 1 electron in the outermost shell, if it has got 1 electron in the outermost shell, what will be its valence? What will be its group? Its group will be also 1. Its group will also be 1 because it has got 1 electron in the outermost shell. Then what will be its valence? The valence will also be 1. So there is a bit of a similarity of a trend there. Number pamwamba, if you have 2 electrons in the outermost shell, 2 electrons in the outermost shell, this element will also be in group 2, and this element will also have a valence of 2. If this element has got 3 electrons in the outermost shell, it's got 3. Therefore, its group will also be 3. The valence will also be 3. But if this element has got 4 electrons in the outermost shell, it will be in group 4. Its valence will also be 4. If this element has got 5 electrons in the outermost shell, if it has got 5 electrons in the outermost shell, it will be in group 5, but its valence will be 5 from 8 to be 3 for the valence. Then, if this element has got 6 electrons in the outermost shell, it will be in group 6. Its valence will be 6 from 8, it will be actually 2. If this element has got 7 electrons in the outermost shell, it will be in group 7, but its valence will be 7 minus 8, 8 minus 7, or 7 from 8, which will give us 1. And finally, if this element has got 8 electrons in the outermost shell, its group will also be 8, but its valence will be 0. Because we are saying For those that have electrons that are more than 4 or more than 3, they're saying that valence is equal to 8 minus the number of electrons in the outermost shells that we are calling valency electrons. So because this gas has got 8 electrons in the outermost shells, we'll say 8 minus 8, which will give us 0. But this is not the case. Is not the case with helium, because if it is helium which only has 2, if you subtract this, we're supposed to have 6. So on helium there, you just have to understand that the helium, a guy has got the valence of 2, has got a valence of 0, because after the first shell is fully occupied, there are no electrons that remain to go in the next shell. So with that, that's where we can conclude our lesson, unless there are questions.
No, there are no questions.
Thank you so much. I will inform you when I'm back from town.
Okay.
Then we'll continue. But for now, I'm going to end the meeting and record the presentation, upload on YouTube. Then I don't know if it's okay, I should share the link again.
Yes, it's fine. You can share the link.
Thank you.
Okay, thank you.